exergy saving in refineries. This is a concept to improve efficiency on CDU furnaces without lowering the stack temperature. I have to apologize, this may be a little bit technical, but I'm here to explain. We have learned in the last few sessions, this is a well-known topic, efficiency improvement, energy saving is a key driver for refineries, and refineries, especially in Europe, are facing a lot of challenges from the outside competition, also internal competition. They are facing price pressure, they are facing environmental pressure, and getting more efficient, more performing is one of the answers to this pressure. There was energy package set up in 2007, and this package was saying we need to improve the energy saving by 20% in 2020. So this target was achieved this year by 22%. As a next step, European Council say until 2030 we need to go to 32.5%. So this puts more pressure again on the refineries, and they have to come up with ideas. So we know that they have got a lot of ideas. There was idea of synergy, ideas of putting petrochemical plant together, partnership. So this is more on the technical point of view, what refineries can do or what they are doing. Also, if you look at the big energy eater in the refinery on a fire furnace, they are improving the heat integration. They are adding heat exchangers, they are replacing heat exchangers by more performing. They are looking to reduce losses by reducing O2 content in the flue gas. They are closing holes, they are putting some better insulation. There are numerous ways of looking at it. My topic will be the obvious, reducing the stack temperature and how does it work. The example is based on the large CDU furnace, fire duty around 150 megawatt. So typically it started in the 80s. You have an air preheater which is here, and it was firing with oil, and the typical outlet temperature is around the 200, 230 in this example. And the typical air temperature was 257. Because it was firing with oil, there was a steam coil here to preheat the air to 50 degrees C. So the heat efficiency is 89.5%, sub duty 136. The first step was to switch from oil firing to fuel gas firing, also lowering the excess air from 20% to 15%. By doing so, you reduce a little bit the flue gas flow, you reduce a little bit on the stack temperature, but there is no significant changes. This is an example of this particular air preheater we are talking about. So you can see it's two big DEKA-type air preheaters, the flue gas coming from the top, one FD fan and going here back to the stack. So it's a very common design. So the next step, people say, okay, we know that we are going to face NOx regulation, we need to reduce the NOx, so let's go to change the burners for, not for dual fuel burners, but for natural gas burners, fuel gas burners. So let's change it. And if we change it, we also know we can drop the step temperature, and let's drop it as far as we can. So this step was to go to about 160 degrees C flue gas temperature. And we also know there is still a couple of sulfur in the flue gas. So in this case, the acid dew point was 111 degrees C. So if you go down with your flue gas temperature, you also need to have some means to protect the cold end of the air preheater by preheating the air going to the air preheater. In this case, we have the same steam coil, but we have added a small hot air recirculation going back to the suction side of the fan. So with this, we get 88 degrees C to the air preheater, and we can avoid corrosion on the air preheater. So this is already a fuel saving of 4.4 megawatt. It's not bad. And this is how it looks like. We still have the same flue gas in the duct, new air preheater. We have added, for reliability, we have added a second fan. We can see here the hot air recirculation going to the suction side of the fan. This is how it looks like in original. But what can we do more? We can drop further the flue gas temperature, and there are ways of doing it by using corrosion resisting air preheater. If you look for a target of 80-90 degrees C flue gas temperature, it's difficult to achieve because you have condensation, you have problem with your ID fan, problem with your stack. You have very often a common stack with several fire heaters. So you have a long flue gas duct. You're not going to change this all just because you do go down with your flue gas temperature. So we came up with a way, and we say we want to keep this temperature same, but we still want to achieve more duty. So how do we do it? We add here some more duty, some more temperature on the air side. We do this by taking waste heat. It can be LP steam, it can be a hot condensate coil, whatever you have, which has not much value. LP steam has a temperature of 150 degrees C, so you can't do very much with this. So we add this heat here. And we also doesn't want to increase the air temperature because there will be maybe increased NOx. So if you have an over duty on your air preheater, you need to take the heat also away of it in some part. So we take it away on this hot temperature section at this place, and this is much hotter. So with this you can take it and put it as on the process heat. So what you do, you take your crude part, you preheat the crude before it goes to your fire heaters, and by this you extract what you put here. You extract on the high temperature side. It's again another 4.2 megawatt. So you trade on one end 4.2 megawatt, which is waste steam with 150 temperature max, and then on the other hand you gain it again, but on a temperature level which on the process side is 240. So this is a huge benefit. It's not only energy saving, it's exergy saving. The exergy is a part of energy you can use. So by trading, you make these fire heaters more performing. So we still have the same duty, 136 megawatt, but the fire duty is now only 143 megawatt. So you came up now with an efficiency of roughly 95% of this fire heater. Of course, this you need to find some heat available in the plant, but I think low pressure steam or hot sun condensate is not difficult way of finding it. So at the end, this is how it could look like. we have our double stage air preheater, and in this part here you can see the coil with the process connections here. So we have the same amount of passes as you have in the fire heater. In this case it was 8 passes. So you can reroute your piping, make some alcoholic valves, so you can always bypass it. And here you have. So at the end, what benefit do you have? First, you're entering your air preheater as 120 degrees C. So you have no problem at all with corrosion. You're above the dew point, so nothing can happen. You can have a carbon steel air preheater. No need for exotic material. Operating cost remains low because you are having LP steam, which normally you don't even know what to do with it. The trade-off is good because you get these 4.2 megawatts on the hot section, so it's a higher exergy value. This is worth 4.3 megawatt of fuel saving, and this also can be applied to all air preheater system regardless of fuel type. You can even use it on oil firing if you have so, because you still have a very high temperature on the inlet side. And if you are smart, you would go from the first step directly to the final step, because then you avoid the cost associated with dismantling installation, so you can get in one giant step, you can have 8.7 megawatt, it's 5.3% efficiency gain directly. So with this last word, 5.3%, I will end my presentation. And the message here is that we know we are living in a challenging world. A lot of things is changing, but we are all engineers. We have a lot of ideas, and we can do a lot of things to make our refineries better. And we have a lot of means to squeeze out more energy out of it. So thank you for your consideration. I hope you will have a lot of questions. So let's start.